Earlier, we discussed how to compute the change in electric potential in situations where the E field is constant. Today, we'll discuss how to handle the more general case of computing the change in electric potential where the electric field changes along some path in space. As a refresher, before continuing with this lecture, you may wish to first view the lecture on electric potential energy, which discusses a particular case where the E field is not constant, the case where the source of the E field is a point charge. We'll build on that example today, but let me emphasize here, there are lots of configurations of source charges, different configurations that lead to non-constant E fields. We'll flesh out the details for the change in electric potential for the case of a point charge as just one example. You'll have the opportunity in group problem-solving sessions to work out the change in electric potential for non-constant electric fields caused by other configurations of source charges. Let's start with the definition of the change in electric potential energy. It's minus the work done by the electric interactions, which we can express more generally as minus the integral of the scalar product of the electric force and the small displacements, vector dr, along some path in space. We can rewrite this expression by remembering the electric force at any point on that path is the product of some charge Q at that point times the electric field vector E at that same point. Remember that this E field is not due to small q, but rather to some other charges, the source charges of the field. Now the change in electric potential, delta V, is obtained by dividing out the charge Q. In other words, the change in electric potential depends only on the source charges as described by the E field, as the E field acts at small displacements vector dr along some path in space. Because we are considering cases where the E field changes along this path, we have no choice other than to work out this integral in order to figure out the change in electric potential. Let's see how that's done for the particular example of a point charge as the source of the E field. Consider a charge capital Q greater than 0 located at a point in space. We know how to write down the vector electric field for a point charge for any observation point located by the position vector r. Let's consider two such observation locations labeled I and F with corresponding position vectors. These locations are the endpoints of some path in space. Specifically, I is the starting point, the initial point of the path, and F is the endpoint, the final point of the path. The change in electric potential, delta V, is minus the integral of the scalar product of the E field times vector dr. In other words, we're taking the scalar product of the vector E at small displacements, vector dr, at various points along the path, and summing up all those scalar products along the path by integrating. Since the source of the field is a point charge, we can plug in our expression for a point charge's E field into this integral. Let's unpack this expression. First, let's note that the magnitude of the vector r can be written like this and represents the radial coordinate as measured from the charge, or in other words, the distance from the charge. The scalar product r hat with vector dr ends up just being small changes of that scalar r, which we'll write as dr, no vector symbols. So using these ideas, our integral becomes this, where we've taken all the constants outside the integral sign. Notice the limits of integration, r sub I and r sub f, are not vectors. They are the distances from the charge for respectively the initial point and the final point of the path in space. This means our integral is a scalar integral, and we know how to do an integral of this form. And when we evaluate this integral at the limits, we end up with this result. Let's notice that if we start near the charge and move further away, that is, R final is larger than R initial, then delta V is less than 0. If we move closer to the charge, that is, R final is smaller than R initial, then delta V is greater than 0. Let's notice all this depends on capital Q being greater than 0 for this case. Also, as an aside, if we move along some path where the distance from the charge does not change, say we move in a circle of constant radius, then delta V is equal to 0. These results describe delta V, the change in electric potential. We can also get at V, the value of the electric potential at a point in this particular example. Let's notice that we can write delta V as V sub F minus V sub I, that is, V at the path's final endpoint minus V at the path's initial point, starting point. Let's expand the right-hand side, and let's notice that on both sides of this equation, we can relate terms with the same subscripts. That is, V sub F with the term on the right-hand side containing R sub F, and V sub I with the term on the right-hand side containing R sub I. This suggests that for a point charge, the electric potential at a single observation location at a distance r from the point charge can be written like this. With this expression in hand, we can now consider the question of what it means to have V equal to 0 for a point charge. Let's notice that for capital Q positive, V can never be negative, and specifically, V approaches 0 as the distance from the point charge goes to infinity. This means that for a point charge, we can think of the 0 of the electric potential as being located at a very, very, very large distance from the charge. One consequence is that we can use this expression to think of V, the value of the electric potential at a point, in a particular way. Imagine starting infinitely far from the charge and moving on a path that ends up at some finite distance from the charge. Then V at that distance r is the same as delta V along a path starting at infinity and ending up at a distance r from the charge. We can see this explicitly. It is just V final minus V initial, where at infinity, V initial is 0. For this discussion, we assumed capital Q for the point charge was greater than 0. I encourage you to think through how things might change for V and delta V if capital Q is less than 0. In particular, for delta V, if one starts at some location and moves further from the negative charge or closer to the negative charge, then ask yourself the question, what is the sign of delta V? For the value of V itself, is V non-negative or non-positive for capital Q less than 0? That's it for this lecture. In our next lecture, we'll discuss a very important property of the electric potential, path independence.